Okay, good morning. Let's get started. So, we are looking at the Thomas algorithm. Or also known as the Tridiagonal Matrix Algorithm. Okay, yesterday we have discussed how kind of this works as a kind of special case of or a modification of the Gaussian elimination process, right. So, let me kind of write the complete algorithm today. So, the first step is to calculate the coefficients Pi and Qi, right. So, the first one is P1. What was P1? P1 was B1 upon A1 and Q1 is how much was Q1? D1 upon A1, is it? Can you help me write this? Was it D1 upon A1? Correct? Okay. So, this is P1 and Q1. Then what do? Then you use the recurrence relations and calculate Pi as which is given by how much was Pi? Bi upon Ai minus Ci Pi minus 1, right, is that correct? Okay. And then we have Qi equals Di plus Ci Qi minus 1 upon Ai minus Ci Pi minus 1, right, is that correct? So, that is what we have. So, essentially for I equals 2, 3 all the way to n minus 1 to n, we are going to kind of use these recurrence relations and calculate what is Pi and Qi, right. Okay. All right. So, then once you have Pi and Qi, what do we do? Back substitution, Pi and Qi is known, set what is Tn, right. You start off what is Tn equals Qn, right, and what do we do next? Use the Ti relations and calculate using back substitution what is the Tn minus 1, Tn minus 2 and so on to T1, right. So, essentially use then the relation Ti equals Pi Ti plus 1 plus Qi, is it? Was it Qi, right? Use this relation and calculate for I equals n minus 1, n minus 2 and so on all the way to 1, right, or 2 whatever. Okay. So, essentially you calculate all the temperatures, that is all, right, you have obtained all the temperatures in the back substitution process. Okay. So, this is the algorithm for TDMA, right, which you can kind of code and it will give you solution much faster compared to the Gauss Seidel, right. Questions on this? Okay. So, would you be able to code this part? The algorithm is already there. You essentially need arrays for your A, B, C, D, which you already have from the discretization, and then you need arrays for P and Q, right. You would need arrays for P and Q, and of course, temperature also would be there, right. So, if you have to write, you have to write a kind of a function that takes in these arguments and calculates what is the temperature. Okay. So, you need a small subroutine or a function that you would write which will calculate this and then give you back the field temperature array. Okay. That is what you would do. Fine. Any questions? No? All right. Then let us move on. So, we will look at continue look at the solution of linear algebraic equations for the 2-dimensional and 3-dimensional situations. Okay. So, that is so this is again solution a kind of linear algebraic equations in essentially 2D. Of course, you can also extend this to you can easily extend to 3D as well. Okay, the same concept you can extend it. Now, as far as the solution of linear algebraic equations in 1D is concerned, we have now learned two methods, right. The first one was what was the first method? Gauss Seidel, right. That was Gauss Seidel, which we call it as a point by point method. Okay. That is because you kind of go from one P cell to the next one and keep iterating. The other one we saw was the Tridiagonal Matrix Algorithm. Okay, we looked at Tridiagonal Matrix Algorithm or the Thomas algorithm, right, which kind of gives you solution in like one shot essentially, okay, by solving this the algorithm that we just saw. Fine. Now, if I kind of want to repeat a few things here so that we can use some terminology. So, in case of Gauss-Seidel, let us say if you have AP phi p equals sigma A and B phi and B plus B, if this is our discretized linear equation that we have, then in Gauss-Seidel what we did was we kind of rearranged this equation for every cell, and we wrote this as phi p, which is the unknown at any cell, okay. So, which is the unknown at any cell, we calculated by writing it as A and B phi and B star plus B upon AP, right, where I have now included a star, a superscript star, which denotes the latest available value. Okay. That means, if we are looking at a P cell, the west cell value could be the one that is just iterated, just updated, and the east cell value would be the one from the previous iteration, right. So, that is what we mean. And similarly, if you are, let us say, going from left to right and bottom to top, the south value would be the one which is just updated, and the north value would be the one which would be updated. Okay. So, that is what we mean by the star. Okay. The star is the latest value of phi and B that is available in that cell. Okay. Excuse me. All right. So, then this is the concept. Now, let us say, how do I now extend it to 2 dimensions? Of course, in both 2D and 3D, you can have Gauss-Seidel as it is. Okay, you can still apply Gauss-Seidel. Only thing is that it will be kind of slow, because the information only propagates by one cell per iteration in Gauss-Seidel, right? Because you have one sweep in which the information goes from one P cell to the E cell after the end of the iteration. Okay, so because information only propagates, okay, this information we mean that the boundary condition information, right, because we have specified some information. So, the boundary condition information that we have only propagates by one cell per iteration. As a result, Gauss-Seidel could be slow to converge for 2D and 3D problems. Okay. So, what we kind of resort to is a method which is a combination of a direct method and this iterative method, that is the Gauss-Seidel. Okay. Now, of course, you are also welcome to develop a direct method for 2D and 3D problems. Only thing is that whatever the Thomas algorithm we have developed, that has to be kind of extended to a pentadiagonal matrix, right. Instead of, if you, let us say if you are looking at a 2D problem, then how does your discretization look like? Your discretization will give you a matrix that has 5 non-zero diagonals, right. Non-zero coefficients on the 5 diagonals is what would be there. So, one way is to of course develop a solution algorithm that is similar to the Thomas algorithm, but for a pentadiagonal matrix, but that would require lot more effort. So, as a result, we will not go into that direction. Rather, we will kind of use a combination of the TDMA and Gauss-Seidel. Okay. So, we would use a combination of these two to solve for 2D and 3D problems or higher dimension problems. Okay. Fine. So, what we do is we call this as we give it a name, we call it as a line by line method. Okay. What we mean by line is basically we choose one particular line and then solve TDMA along that line, thinking that that is a 1D problem. Okay. but with the coefficients taken from the 2D discretization, okay, and then we move on to the next line and so on until we finish all the lines in the particular 2D domain, okay. So now if I were to draw, so I am drawing lines that connect the P cells or E cells and West cells, all of them, and I am using different colors for different lines, okay. So essentially we have, let me use wax, okay. So essentially, okay, so this is my x axis and this is my y axis, and then we have some grid lines here, okay, and then we have some grid lines in the vertical direction as well. Okay, so we have some mesh here. Now, these cell centroids that we have here, these are all the cell centroids. Okay, this is, we are looking at the cell centroids is where these junctions are, fine. Okay, that means my actual cells are, for example, if you are talking about a P cell, the P cell is somewhere here, right, and the E cell is somewhere here. This is the West cell. So we have kind of connected all of these using these lines as the lines that connect the cell centroids, fine. Now we have two sets of lines, one is the black lines which are horizontal, and the set of lines is vertical, which are the red lines. Now what we do is we select, we kind of solve the TDMA along the red lines, okay. So essentially solve TDMA along y direction, okay, along the red lines, and use Gauss-Seidel along the x direction, fine. So that is what we mean by a line by line method. We go from one line to another line, and then I would use another kind of terminology here, which is, I use two terms, one is called traverse direction and the other one is called sweep direction, okay. Now what we mean by traverse is the direction in which the TDMA is applied, okay. So this is the TDMA direction. In this particular case, the y direction happens to be the traverse direction, and the sweep direction is the direction in which these lines are progressed, okay. Let us say in this particular case we move from x min to x max, we go from 0 to x max, so we are going sweeping in the positive x direction, okay. So that is essentially the direction in which your Gauss-Seidel or the lines are visited, okay. So this is the direction in which lines are visited, okay. This happens to be the x direction. Okay, now the question is then, how do I solve TDMA along these lines? That is very simple. If we look at the discretized equation, what would a discretized equation look here in terms of ij, if we indicate I and j as the P cell? So what I have is, I have a ij, phi ij would be my unknown for the P cell, right. This is like a p phi p equals sigma a and b phi and b plus b. Now on the right hand side, what do we have in terms of I and j indices? That would be some a I j plus 1 phi I j plus 1 plus some b I j minus 1 phi I j minus 1 plus what else do we have? Plus some c I plus 1 j phi I plus 1 j plus d I plus 1 j phi I plus 1 j, I am sorry, it should be minus 1. So this is I minus 1 j and this is I minus 1 j, plus we have some, what else, some constant, let us call the constant as e I j, okay, that is our d, our earlier d. So we have essentially links to east, west, north, south and the source term, right. So we have all these things. Now we want to apply TDMA along the y direction, right. So if we want to apply TDMA along the y direction, like along this direction, that means the coefficients a, b, c, d, or what would be unknowns if I want to apply along the TDMA along the y direction? What will be my unknowns? Ij, would this be an unknown? Yes, this is an unknown, okay. So this is an unknown. What else would be an unknown? Ij plus 1, right. So this would be an unknown, and what about Ij minus 1? Is an unknown as well. So essentially along the y direction I have all the unknowns aligned. Now I kind of pretend that all the values on the left hand side and the right hand side are known to me, okay. Those are the latest values or the guessed values, they are known to me, okay. That means I am not solving for them along this line. Along this line, when I am solving for TDMA, everything else is known to me, right, other than what is aligned along that line. That means I can write phi I plus 1 j with a star, okay. The star means that it is the latest value that we know, and phi I minus 1 j is also with a star, okay. That means if I look at here, so your this is your phi I j, right. So essentially these black lines, these black dots are where the unknowns are aligned, and the crosses are where the values are assumed to be known, right. So these are assumed to be known for the purpose of this iteration, and these are the values which are unknowns, right. So essentially now we kind of came back to a 1D situation from a 2D situation. Now can you extend the same concept to 3D, right. So we have one line and then you have 4 neighbors, right. So you have 2 more terms which are on the top and bottom, they will also be treated as knowns, right, they will also be treated as known values. Fine. Then I can rewrite this equation as Aij phi ij equals Aij plus 1 phi ij plus 1 plus Bij minus 1 phi ij minus 1 plus some Gij, where Gij consists of what? Ci plus 1 j phi I plus 1 star j, di minus 1 j phi I minus 1 j star, and Eij, right. All these terms together is nothing but Gij. So Gij is a known value, right. Okay, now can we apply TDMA for this line, right. I can apply TDMA along this line and then solve for all the phi values in one shot, right. Okay, and then I move on to the next line. So essentially we solve it for let us say this is the first unknown. So we solve TDMA along this line with guessed values, and then we move on to the next line. So when we move on to the next line, what do? We update the phi values that we have just found for these points, right. We update them and then we move on here, then we calculate these values and then we move on to this particular line and so on. So our traverse direction is in the y direction and the sweep direction is in the x direction, the direction in which the lines are visited, okay. Now you may have a question like, why should it be y direction, why should it not, why cannot have x and y interchanged? You can certainly do that, you can interchange x and y directions, the sweep and the traverse directions, that is completely possible. In fact, we will also see a kind of intelligent way of doing these things such that we kind of get convergence faster, okay, that is also possible. Now okay, so that is line by line TDMA. Now questions on this part. That means once you have a line, if you have a TDMA solver, you can easily now extend it to solve 2D and 3D, and this will be much faster, okay. We'll see in a little while why it is faster than Gauss Seidel. Yes, right. Okay, why do we say so? The Gauss Seidel, the question is TDMA is quite visible because along the y line, but however, where is the Gauss Seidel coming into play here? So the Gauss Seidel is coming into play in terms of convergence. So essentially you sweep along one y direction, right, and then that is not the correct, that is not the final answer, right, because we have started off with guess values on both sides. So we are updating those line values and then we are moving on to the next line, right. So essentially imagine if the y direction was not there, if this was just a 1D with only x directions, then you are sweeping in the x direction. Do you call that a Gauss Seidel? You are moving from point to point. Here only thing that you have collapsed the y line using a direct solver, right. So all these values you got for all the cells in the y direction, we are just updating them and then moving on to the next set of lines, okay. And then you have to keep doing this process until you converge to phi values for the entire cells, all the range of cells, right. Do you agree? If this was a direct solver in 2D, you do not have to, you just calculate everything in one go, right. Here we have kind of a Gauss Seidel sweep in the x direction and the TDMA is in the along the y direction. Does it make it clear? So essentially let us say, what do I do? Let us say if I write a kind of pseudocode for Gauss Seidel. How do you write a pseudocode? Essentially, you loop for sum for equals 1 to I equals n, right? You kind of go through each of these things and you update what is phi I from these values, and then you would check for convergence, right? That is what you would do, right? This is what you do in a Gauss Seidel. Now, in this also in 2D you are doing the same thing, but instead of calculating phi I directly from some expression, you would call what? You would make a call to TDMA function, which will give you, instead of phi I, it will give you phi I for the entire range of n cells, right? It will give you for all the cells in one go, and then you would move on to the next line and so on, and then you would still check for convergence, okay? So, that is kind of a line by line TDMA, you kind of check for convergence as well. So, using the guess values while calculating the TDMA is where we call it as a Gauss Seidel, okay? It is kind of implicit in there, but not exactly like Gauss Seidel, okay? Okay, so yeah, so the question is if I have any iterative method, I would call it as a, it is valid for anything, right? Essentially the convergence checking and the iterations. And why is it called Gauss Seidel? The question goes back to the difference between Jacobi and Gauss Seidel, right? Essentially we have, if you are updating after you calculate, you call it as Gauss Seidel, or if you are not updating, you want to keep those previous values, then you call it as a Jacobi method, okay? I mean, of course, you are welcome to name it anything, but that's how, it's not how it is, okay? Other questions? You will be able to write this. Like essentially what I want you to do is maybe in the next assignment, you would first develop a TDMA solver for 1D situation. Now that has to be generic enough such that, so you have to write some kind of a function or a subroutine for solving TDMA, okay. So don't write it in the main program itself. So you write a separate function because you would be calling it many times, okay, and you would be using this 1D thing in 2D and 3D situations later on, okay. So TDMA, what all you want to pass it to? So now the TDMA should be generic enough such that you can either run it along y direction or along x direction. So first thing you want to know is how many cells I want to kind of use, right, and then you have to pass the coefficients, that is an, bn, cn, right, and dn. So you have to kind of somehow pass all of these arguments. What else? Do you have to pass pi and qi? No, you can calculate them inside from ABCD. What else? You want to also send what is the unknowns, right, Tn, that is all. So essentially this function takes in all these arguments and then it will kind of calculate what is P of n and Q of n can be calculated, and finally obtain values for Tn using TDMA, right. Now if you have to write a 2-dimensional situation, depending on the number of cells you have in x and y, you would send those particular ABCD, right. Your D would either depend on, D would be either, it would be either these 3 together, or it would be these 2 plus this one together, depending on the direction, right. If you are sweeping along, traversing along the y direction, then these 2 would be there, otherwise it will be the other ones, right. So accordingly you would pass to the subroutine all these values, and then you will be able to traverse and sweep in any directions that you wish, that you choose, right. Now this TDMA function that you would write would become part of a bigger function that would be kind of a what? Kind of a Gauss Seidel, right. So essentially this guy would be called here, right, within your Gauss Seidel. Fine. Is the traverse and sweep make sense? Okay. Those are, so the I minus values are known when we are iterating, yes. So either they happen to the boundary values or they happen to be the near boundary or whatever, right. Well, yeah, I mean, so yeah, I think the question is again, why is it Gauss Seidel? I think you are not happy with the word Gauss Seidel. So the thing is, we just have values. Think of a 1D situation. You have some cells and you calculate the value at P cell and you move on to the next cell, right. That is what you do in a Gauss Seidel. The same thing is what we are doing in the line by line TDMA, except that instead of calculating one value, you are getting values for a row, right, for the entire y values, and this is what we are getting in one shot through TDMA. Okay, that is why I call it as Gauss Seidel, but we can just say line by line TDMA, okay, if you are not happy, okay. Other questions? No, you will be able to, yeah. Solve one example for TDMA. Okay, that's a tall order. I can't solve it in the class. So that will be your homework. Okay, if you have questions, I'll explain with that. Right? So maybe we'll spend 2-3 weeks solving TDMA in the class. Sorry? Just one iteration TDMA. I mean, yeah. So he says essentially just make the matrix and then substitute. I don't think we have to do it. Essentially, you have. So I have the. Essentially, it is this one, right? Calculate B1, D1. If you want, I can set up a problem and solve it. Maybe sometime next week or so. Okay, but it's probably not required. You know, because I want you to do the rest of the things from here. Okay, fine. Would you be able to do decode these things? Right. So we can do one example, but I think that's your learning process. Okay. Other questions? It's very straightforward, right? Just calculate PQ, and the algorithm is solid, so you just have to go through all these steps. Yes. How phi I plus 1 j is an updated value? No, phi I plus 1 j is not an updated value. So this is I plus 1 j here. The question is, how is this an updated value, right? This is not an updated value. This is a value from the previous iteration. That's all. So we are pretending that that is known from the latest value because we are solving along the line, right? Yeah. So that so the question is, how slow Gauss Seidel would be compared to TDMA? That depends on the problems, okay, of the size of the problem. As such, we will come to that in terms of. I don't have numbers as such, but it will be much slower. No, okay. So let's kind of have a discussion or comments. So essentially, your TDMA, or we will say the line by line method, okay, is much faster than Gauss Seidel in, let's say, Gauss Seidel in 2D problems or whatever, because the boundary condition information propagates in one go, right, or at once to the interior cells. Yes. Aij, Phi, yeah. Coefficient of Phi, this one. Oh, I'm sorry. I should have written B. Yeah, you're right. So let me just change it to. So the question is, the coefficient should be different. Yeah, this is. It should not be. This should be something else. Let me call it as central. This is maybe. Let's call it as a Pij or something. Okay. This is certainly not the same. Something else. Okay. But that doesn't make a difference anyway. The coefficient for ij and ij plus 1, right? I have the subscript anyway there. Okay. So I should have started with B, C, D instead of A, B, C. Okay. That's fine. Yeah, of course it is different. Fine. Other questions? No? Okay. So what I just wrote here is, I say the line by line method is much faster compared to Gauss Seidel if you go for, let's say, 2D or 3D problems. That is because in the line by line method you are actually using TDMA, which transmits the information of the boundaries into all the interior cells in one go, right, at once. You don't have iterations, right, whereas in Gauss Seidel the boundary condition information is updated to the cells by one cell per sweep, right, because if you have done one sweep, then the information would have moved by one cell, right, from left cell to right cell and so on. So that's why the line by line method would converge faster than a pure Gauss Seidel. Okay. So LBL, which is the line by line method, converges faster than Gauss Seidel because of the information being sent across, the boundary condition information being sent across at once. Okay. Now, of course, the traverse and sweep directions can be interchanged Okay. For example, for let us say for one iteration you could use a traverse in the y direction, and the next iteration you could use a traverse in the x direction. Okay. You could kind of interchange the sweep and traverse directions to increase convergence. Essentially, because the TDMA sends information of the boundaries very quickly to the interior, if you exchange the direction, then the information of the left and the right boundaries also would come into the interior much more quickly. Okay. So, as a result, instead of just sweeping in the y direction, let us say for 100 iterations, you could actually, what you can do is you can just exchange the order of the sweep and traverse. That means, initially you can go with this is the traverse and this is the sweep, and the next iteration you could actually do this is the sweep and your traverse could be along x axis. Okay. You could do this. So, essentially your sweep is in this, your sweep is along this direction here, and your sweep is along this direction here. Okay. Along x and along y. So, you could even alternate this because the TDMA will bring in the boundary condition information to the interior cells in one go. Okay. As a result, you would get convergence much faster. Okay. I will try to, I think your next assignment would kind of involve these things. Okay. So, your TDMA function has to be generic enough such that you can do all these patterns. Okay. You could do left to right and then top to bottom, or you could do just a top to bottom, something like that. Okay. Or bottom to top, all these things. Fine. So, that kind of patterns can be used to increase convergence. Okay. Now, sometimes the geometry and the properties would kind of dictate the direction of sweep, direction of traverse or sweep. Okay. So, what do we mean by geometry and the properties? Okay. Essentially, what we mean by this is, for example, let us consider you have gamma east, gamma west, and you have gamma north and gamma south. Okay. So, the diffusion coefficients, let us say the east and west diffusion coefficients are much larger than the north and south. Okay. That means, these are much larger than this. What would, and if you have a kind of a uniform mesh, okay, or uniform cells, then what would be the coefficients A east and A west in comparison to A north and A south would be? These would be larger, right? These would be larger. As a result, you would like to choose the traverse in which direction? In the east west direction, right? That is clear. You want to choose traverse in east west. Why is it so? Because the coefficients are larger, because the boundary condition information will come in quickly, and what else? Because A north and A south are so small, the errors that you introduce by guessing the values would be insignificant compared to what you would have from A east and A west, right. So, as a result, you would kind of go along, traverse along the x direction, right, because the guess values you would use in the north and south directions. So, the phi along phi star along n and s would have insignificant effect on AP or on phi p, right. So, as a result, traverse should be along x direction. So, or in general, traverse should be along the direction in which you have larger coefficients. Okay. So, it should be along the direction of larger coefficients, okay, because the small coefficients would not change it much in terms of the solution convergence. Yes. Okay. The question is it a rule for faster convergence, or does it make the matrix better, right? This is essentially only for faster convergence, because as you can see, the AP, of course, it would also depend on the A north and A south coefficients, but I do not think the diagonal dominance would increase because you have chosen it this way, right, because you would have a source term. Essentially it is for faster convergence, fine. Other questions? No, okay. Let's then what about the properties? So properties is done. What about the geometry? We said two comments, right? One is geometry, the other one is properties. These would kind of indicate that we should choose the traverse in a particular direction. Coming to the geometry, let us say we have a mesh that is very with a large aspect ratio. Okay, so essentially I have very thin cells, which is quite possible in several applications. Okay, so we have a mesh that is like this, which is really thin. Okay, I just made it non-uniform because I couldn't draw them much better. Okay, so this is what we have, and the cells are like this. Okay, so these are the cells. Okay, so this is my P cell. This is east, this is north, this is west, and this is south. Okay, so we have delta x, which is much larger than the delta y, and we also have the del xe and del xw, and we also have the del y north and del y south. Okay, so you can see that delta x is greater than delta y, somewhat greater, 3-4 times, and delta xc, delta xw also 3-4 times greater than delta y north and delta y south. Okay, so then how do the coefficients look like? If I look at A east and A north, okay, one for each direction. A east would be what? Gamma east. Let us say the gamma is the same everywhere. Then what would be A east coefficient? AE delta y by del xe, and what would be A north? Gamma north delta x by del y north. So which is now greater? So which is now greater, and in what direction would you choose the traverse? AE, is it greater? E is smaller, east west is smaller because delta y is small, this is small, and this is delta xe is large in comparison to here, which is larger, and this is smaller, right. As a result, the north coefficients would come out to be larger than the east and west, right. So in which direction would you choose the traverse? In the y direction, right. Essentially that is going to, so your traverse would be along this direction, this is your traverse direction, and your sweep would be in the x direction. Okay, fine. So essentially you choose it along the larger coefficients. Now these are all only kind of tricks for little bit faster convergence, that's all. Now these would help you, especially if you have a big 3-dimensional problem or a big 2-dimensional problem, right. And if you have unsteady as well, then you have to kind of solve all this for every time step. Okay, in that situations, cumulatively you will have a much quicker solution obtained if you make use of these tricks rather than blindly just running it with a Gauss Seidel, something like that. Okay, so the question is if you use TDMA along the more number of cells, which is the y direction, you may run out of RAM, but yeah, I mean, if you have some technical problems, then you have to accordingly change it. Fine, here we are assuming that we have enough RAM to run. Other questions? Okay. All right, then we looked at the comments, then let us make a statement about few more things. Essentially, we looked at the geometry and the properties, okay, both of them. We talked about the traverse direction based on the coefficients. Now similarly we can also have dependency on the sweep direction. Okay, the sweep direction also could be dictated by the geometry that we have. Now how do we say this? For example, let us say I have coming to the boundary conditions, let us say we have a domain like this, rectangular domain, on which we have some isothermal boundary conditions on the 3 faces, and then on one of the faces on this side we have an adiabatic boundary condition. Okay, these are the boundary conditions that we have. In this scenario, how do we choose the sweep direction? usually you start off sweep from the direction where you have a known boundary condition, like a Dirichlet boundary condition. Okay. So, the sweep direction should be from left to right. Let us say if I am using my traverse is this direction, this is my traverse, then my sweep would be from left to right, because as I am sweeping, I am starting off with a known temperature, and that would be brought in inside. Okay. But if I start from right to left, then because it is adiabatic, I do not have a temperature, right. So, the information of the isothermal boundary condition or something like would not be brought in very quickly, right, because this itself is not a fixed value. Okay. As a result, this if a sweep in the other direction from right to left would be kind of slower than a sweep in the from left to right. Okay. So, now these are all kind of observational things. So, if you write a code which you would in the assignment, and then you can kind of play with them and then add it up with this insight that we are getting here. Okay. So, essentially you should always start the sweep kind of should bring known values. Okay. So, essentially that is in the direction of the known values. Okay. That is what we would do. Now, for example, let us say if you have convection, let us say there is a flow that is going in this particular direction, let us say there is a flow, then how would you sweep? Would you sweep in the direction of the flow, or would you sweep against the direction of the flow? Let us say flow is happening from left to right, what would be your sweep direction? Left to right, you should go with the flow direction, because then you have information coming from the flow, right. So, you should always go in the direction of convection for your sweeps rather than against. Okay. If you go against, will the problem converge? It will still converge, you may be doing some more iterations, that is all. Okay. So, convection then sweep in the same direction. Okay, as convection, fine. So, these are essentially some tricks by which you can choose the direction of the sweep and the traverse, fine, which will kind of help you get a faster convergence than if you had chosen it without these things. Okay. Questions? No questions? Okay. Yeah. Number of cells, yes. Do the number of cells affect the direction of sweep, is it? So, question is, okay, if you have more number of cells, should I choose it that way? That is possible, but usually you would not have, I mean, depends on the problem you are solving. Okay. Ideally, because this TDMA is only a 1D problem, so it would not make a lot of difference if you have 100 cells or let us say 500 cells or so, right. It would still come out very quickly, right. So, there are a lot of things which we can affect here, but these are some broad ones. Okay. Certainly number of cells and the aspect ratio, all these things will definitely affect how fast it can kind of converge. Okay. Other questions? So, the takeaway is you have to write your subroutine such that it is generic enough and you can play with it. Okay. Sweep and traverse you can kind of alternate, or you can kind of call it in x direction as well as y direction and things like that, fine. No other questions? Okay. Then let us move on to one more thing, that is basically source term linearization. Okay. Fine. So, we have always said if there is a source term S of let us say temperature or something, S of t, which is a nonlinear function of temperature. Okay. S of t is a nonlinear function. So, it depends on t square t cube and some constants, etc. So, we have a nonlinear source term, right. Then we always said we have to kind of linearize it. And we said S of t would be linearized as some constant Sc plus Sp times Tp, right. So, essentially we have a linear model for this nonlinear source term, right. So, we have a linear model. okay, then the question is why do we have to linearize, and if we have to linearize, is there a good way of linearizing the source term, right, or can I linearize it in infinitely many ways? The thing is, we have to linearize because the ultimate system we would get is a linear system, right. The entire framework is essentially you would get Ax equal to b, right. So, you cannot have a non-linear thing within there, right. Your x is always linear. So, essentially the nominally linear framework only allows for linear models to be there, okay. That is why we that is why we must linearize the source terms, right. And the second thing is linearizing it is better than just having a constant in there, right. You could also say I would use a constant for the source term, but linearizing is a better model compared to just having a constant source term, okay. So, linearization is better than just a constant, okay. So, these are the two main motivations to linearize the source term and use it in the fashion that we have discussed. Okay. Now, so the general one of the general way to linearize any source term is to use Taylor series expansion. Now, of course, the linear model that we get should be a SC plus SPTP. This should be a good representation of the original nonlinear function, right. It should be somewhat a good representation of the original nonlinear function, and it should also satisfy the SP less than or equal to 0 condition, right. This we have kind of stated. So, if these two are there, then the linearization model we would use would be kind of a good model, okay. So, a general way to do is using Taylor series expansion for the source term. That means, if I have some S of t, I would write it as S plus partial S partial t times t minus t star, okay. So, these are all evaluated. So, essentially I have some S star, I am expanding about S star, expanding about star values, okay. What are star values? Known values, okay. We are expanding about the known values and then obtaining a model for our nonlinear source term, okay.